Kinetic energy is the energy of an object in motion. If you have an object that is moving along with some velocity, the kinetic energy is calculated by taking 1/2 the mass of the object times the object's speed squared. If an object is moving, it has kinetic energy. If it's not moving, it has no kinetic energy. So this is often called the energy of motion. Calculating kinetic energies, it's important that you know that all masses must be in kilograms and all speeds must be in meters per second if you are to get this to come out into the unit of joules, which all energy has. So it's important that you use the right units when you calculate this thing. So one of the things you might be asked to do is ask conceptual questions about kinetic energy. For instance, what would happen if I had a car and I doubled its speed? What would happen to its kinetic energy? And the answer is that you would take that formula, you replace everything that doesn't change with a 1, and the thing that does change you replace with that number, and then you perform the operation. So in this case, we would come up with a 4, which means that doubling the speed of an object would quadruple its kinetic energy. Tripling the speed of an object would give you 9 times the kinetic energy. Now, in the last video, I promised you that we would find an application for work. And the first application of work is this idea called the work energy theorem. The net work done on an object is equal to that object's change in kinetic energy. So therefore, if I go kick a soccer ball and exert a force on it for a distance, I will then have changed its kinetic energy. If it started at rest and had 0 energy, it would wind up with some amount of kinetic energy that was equal to the work that we did. So that's the work energy theorem. The applications of this are where it can get kind of tricky. For instance, if I replace work with force times displacement, and let's assume that the object's force is in the same direction as its displacement, so we can forget the cosine business for now. This would be equal to change in kinetic energy, which would be my final kinetic energy minus my initial kinetic energy. And one of the things that we often do with this is we could be given a force and a distance and be asked to solve for how much the speed would change. If we knew the mass of the object, we could do that by solving this thing for that. Other things we could do is we could give you information about, say for instance, a car is speeding along down the highway with a certain given speed and a certain given mass, and let's say I knew the amount of force that would be applied to this car when slamming on the brakes. And the question might be, well, how much distance does it travel when that happens? And if we take this relationship that we have here, we can see that solving this for the distance, we're going to get the change in kinetic energy over the force. If we're stopping this car, the final speed is 0. So we wind up with an expression that involves that mass and velocity and force that we were given. Another thing that you might be asked to do is to look at it in this way. Let's say I had a car that was moving like we just discussed, and let's say we're going to stop that car. And so we know that because the first term goes to 0, that the work done will be equal to minus the amount of initial kinetic energy it had. Minus work means that we're taking energy away from something. So it makes sense if the car is moving down the road with kinetic energy and we stop it, we've taken away its kinetic energy, and that's why our work should come out to a negative number. But let's say, for instance, we wanted to look at this conceptually, and we were given a question like, what would happen if we had a car that took, say, 60 meters to stop by slamming on the brakes, but then we double the speed of that car? If we double the speed of that car and the force of friction remains the same, how much distance is it going to take for that car to stop? And you can look at this the same way we looked at the definition of kinetic energy, except for now that we know that that kinetic energy is equal to the work that's being done. And so if I was to solve this thing for the distance, like it was over here, and I'm just going to rewrite it, and do my thing where I say, okay, everything that didn't change is going to get replaced with a 1, and the thing that did get changed, I'm going to replace with a 2 because we're doubling that speed. I would wind up with 1 times 1 times 2 squared over 1, which is 4. Which means that if I double the speed of a car, it's going to take 4 times as much distance to stop as it did before. And so you can see why speeding is such an issue, because if you go faster and faster and faster, you're exponentially increasing the amount of stopping distance that is required to stop your car, which is why speeding is dangerous.